Going on, guys, let's do this problem right here. The question is asking the PV diagram shown below applies to 2.1 moles of an ideal diatomic gas. Calculate the temperature at all points and calculate the heat transfer in paths A, B, C, C, D and D. So let's do the first question. Calculate the temperature at all points. So let's begin with A, but before I do that, let's convert these into liters. So we know that 1,000 meter cube is equal to 1000 liter, right? So here we have 0.01 meter cube, so that's going to be equal to 10 liter. And here we have 0.05 meter cube, that's going to be 50 liter, right? So we have this information. Now, how can we find the temperature? To find the temperature, we can use the ideal gas formula, that is PV is equal to nRT. So let's begin with A. A, we have the volume, that is 10 liters. So let's start with the pressure, that's 5 atm. So 5 multiplied by 10 liter. 10 liter, N is 2.1 mole. 2.1 mole. So since we are using liter and atm, we have to use this R right here. This is 0.08206. So this is basically liter atm mole per mole Kelvin, right? So that's why we use this one. If you use Pascal and meter cube, you have to use different, like 8.321, that R value. Here we are trying to find the temperature, and if you rearrange this one and plug it in calculator, you will get 290 Kelvin, right? So this is the answer for this one, 290 Kelvin A. So A is let's say TA, right? So let's look at the D right here. And here if you see, this is 10 liter and this is 50 liter. This is like 5 times bigger, right? 10 liter, 50 liter. So if you notice that volume is directly proportional to temperature, so when the volume increase, temperature is going to increase. So here what's going to happen is, if you have 290 Kelvin at 10 liter, at 50 liter, this is going to be 5 times of this value right here. So if you multiply this one by 5, you will get the answer for TD. But let's do this one by this equation. This is PV is equal to nRT equation. That is at D point we have 5 atm. 5 atm. This is 50 liter. That is and also we have the mole, that is 2.1 multiplied by 0.08206 times T. And if you calculate this value, that's going to give you 1450 Kelvin. Also, if you multiply this one by 5, you will get the same answer. So that's how we can find the TD. And let's look at B now. Let's see what happens right there, right? So we are trying to find the TB. Also, if you notice, this is 5 atm, this is 40 atm. So according to this formula, we know that when P is increased, T also going to increase, right? And if you look at the ratio, that 40 divided by 5, that's going to be 8 times, right? That's going to be 8. And if you multiply whatever the value you got in A by 8, you will get the same answer. You will get the answer for the temperature at B. So let's do that one and see what we get. If you multiply this 290 by 8, you will get 2320 Kelvin, and that's going to be the value at B. Let's look at C. C, if you see that this also 8 times. If you calculate D, we have to look at the volume at that point, and if you calculate, we know that point D is 1450. And if you multiply this one by 8, that's going to give you the value of T at point C. And this is 1450 times 8 is going to give you 11,600 Kelvin. So this is going to be the answer for TC. So now we found out all the temperatures. Temperature are to all points. So TA is this value, TB is this one, TC is this one, and TD is this one right here. Now they are asking calculate the heat transfer in points A, B, C, D, and DA. So how can we calculate the heat transfer? So let's see how we can find this one. So first let's begin with AB, right? So here we have this one AB. Since it's an isochoric process, we know that volume is same. So isochoric process, whenever we have isochoric process, we can use this equation NCV delta T. If it's an isobaric process, if the pressure is constant, we use CP, right? For an they are saying this is an ideal diatomic gas, right? For an ideal diatomic gas, this is going to be the CV value is going to be 5 by 2R. This is always true, right? So here that's what we are going to use. We know that mole is 2.1, and this is going to be 5 by 2 times 8.315 3145, and if you calculate this value, you will get, also we have to multiply by temperature difference. So here we are trying to find ABQ AB. So at B, what is the temperature? At B is 2320. 2320 minus at A we have 290. So 290, and if you multiply these values, you will get 88,600 joule, and that's positive. So this is going to be the answer for QAB. So let's look at QBC. QBC, you can already see that is an isobaric process because pressure is constant. So here we can use NCP delta T, right? NCP, N is going to be 2.1, and CP is going to be different from CV. So this is CV for diatomic gases. CP for diatomic gases is going to be 7 by 2R. So this is going to be the CP. So here we are going to use the CP. CP is going to be 7 by 2 times 8.3145 times 11,600 minus 2,320, because that so we are looking at BC, right? Point C we have 1,600 and B we have 2,320. So that's how we got this value right here. If you calculate this one, you will get 567,000 approximately. So this is the value you're going to get. And then let's move to the QCD, right? So let's separate this one. So let's round our answers. So this is AB, QAB, and this is QBC, right? Now we are trying to find QCD. QCD, right? To find the QCD, let's see, QCD and isochoric process, because the volume is same. So here we can use this equation, QCD. So this will work. NCV delta T. Since it's an isochoric process, you can use this one, or you can use a different equation to find this one too. Like you can use this equation also, like QCD is equal to VCV delta P divided by R. And we know that for a diatomic ideal diatomic gas, CV is going to be 5 by 2R. So we can replace this one by that value. That's going to cancel these two R's right here. So let's plug the values and see. 50 volume at so we are looking at CD, right? CD, yeah, that's CD, volume is 50. And then CV is going to be 5.2 R times delta P. The pressure difference is going to be 40 CD, so 5 minus 40, that's going to be negative 35. Negative 35 divided by R. And here we can cancel these two R's right here. And if you calculate this value, you will get, and also we are using liter and ATM, right? So we have to convert this one into joule. To convert this one, we have to multiply this one by 101.3. And let's calculate this one. If you calculate this one, you will get negative 443,000 joule, right? This is our QCD. And let's go to the last one, that's QDA. QDA, and if you notice that one, this is an isobaric process because pressure is constant. You can use this equation right here, the one we previously used, NCP delta T, or you can use different equation too, like this one. For an isochoric, we use BCB delta P. For an isobaric process, we use PCP delta V. Only the P and V are shifted. Here we have delta V. Here that's the difference, right? Divided by R. So that's the only difference. And here we know that Cp for ideal diatomic gas is going to be 7 by 2R. So again, the R and R is going to be cancelled. So P dA. So dA, we have P 5 atm. 5 times 7 by 2 R times delta V. Delta V is going to be pressure difference, dA, going from dA. So A minus D. A is what? 10 liter. 10 minus 50 is going to be negative 40. So negative 40 right here divided by R. R cancels. And if you also, this is, we are using liter and ATM. So we have to convert this one into joule. So here we have to multiply this one by 101.3. And if you calculate this value, you will get negative 70,900 joule. And that's going to be the answer, right? Now we have calculated everything. Let's round the final answer. So this is our QCD and this is our QDA. And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.